Welcome back to Module 2.2.2, where we talk about soil erosion. And so in this module, we'll discuss a few of the things, some of the mechanics, and how soil actually erodes. And mostly we're going to talk about the universal soils loss equation and how we can kind of determine what our potential soil loss is. We're running into an issue where we're starting to degrade our lands faster than we can actually replenish them. And so that's kind of really what the universal soil loss equation at least gives us an idea of, is how much soil are we losing and at what point will we run out of soil faster than we can replace it. And so there are several components or causes as to why we are degrading our land. And so most of that is going to be overgrazing. We're just improperly grazing our lands. Deforestation, this one kind of makes sense, right? That if we take out the trees, and I want you to think about, let's go back to Module 1 or 2.1, where we talked about the three different types of interception, where we have stem flow, through fall, and canopy drip. If we don't have any of those trees, that water hits the soil and is not slowed down. Ag activities, this is going to be us. They are pointing to agricultural activities. We're tilling our lands. We're not growing cover crops in the winter. That soil is eroding. We have bare soil. This gets all back to that component of regenerative ag. And then there are some other things that are causing this land to degrade, but they're looking mostly at these three components. And overgrazing is also part of ag activities if you think about it. These are going to be the biggest ones as to why we're degrading our lands. So there are two types of erosion. There's geological erosion, which is natural. This happens over time. We don't really play a role in that. Some of these, many of us have seen these cool structures out in the Midwest, out in the West. Like the Grand Canyon is part of geological erosion, or maybe there is some glacier that kind of paved this highway and moved that soil. We have wind erosion that kind of gives us these very cool swooping rocks. Look, you can see this is more of a sedimentary rock. So there's been layers and layers kind of put on top of each other, and then the wind has come by and eroded and kind of shown us the face of that. So like erosion happens whether we do anything about it or not. So it can't be stopped, but it also can be accelerated, and so that is kind of where humans come in, and this is what we are responsible for. So here's our overgrazing, here's our deforestation, and then finally our ag activities. Plowing while it's dry like this is probably not the wisest thing. Some of us might have seen, if you don't have any cover on your field, this soil is going to, kind of be lifted up and then moved away. And so, this is a big deal, mainly because we're losing some of that topsoil and organic matter, as we just described, or just talked about in 2.2.1, that we want to keep that topsoil there, and we're going to kind of want to improve the soil health and the organic matter that's in there. And so if our soil is gone and we've removed that organic layer, and we've starting to remove some of that A horizon, as we get down into the B horizon, that's compacted. It doesn't have a lot of infiltration, and the pore space is probably small. So we're not going to have a lot of percolation or movement through that soil profile. The CEC is likely to be different. So if we kind of remove the top portion of our soil or our field, then, we're losing a lot of the productivity. And then another thing is that this sediment actually pollutes our waterways, and it is the greatest pollution of those waterways in that it decreases the water quality. And then also that the nutrients that are attached or, held to that soil colloid as that moves into the waterways, that is also adding to eutrophication. This This is costing us money at some point in time for having to try and clean that up, minimize that, whether it be some some filtration system, or having to build a dam or a reservoir so that it can be, let that soil settle out before we continue to move that water throughout that watershed. All right, so we have three mechanics of erosion, and I just want to make this very clear. There are differences between the mechanics and the different types. And so the mechanics are like the physical movement of the soil. Mechanics are the physical movement of the soil. And so there are three mechanics of water erosion. We have detachment, transportation, and deposition. Transport, transportation, and then deposition. So the rainfall is going to hit that soil. If there's nothing to, if there's no interception, if we don't have a cover crop on that, that's basically just pounding that, pounding that soil. There's going to be this detachment or this explosion kind of shown right here. There is some soil. You can see that in this kind of splash, that there's some soil that is now held in suspension and is now moved with that water down to a lower spot and then deposited. And so this might be in a bottom, or even making it to the riverbed. All right, so those are the mechanics. We have detachment, transportation, and deposition. And so those raindrops are falling, pretty fast, pretty quickly, depending on, the intensity of that rainfall and the wind. But generally we have about 18.5 miles per hour. So you have to think about a raindrop hitting bare soil at 18.5 miles per hour. That's likely going to cause a big splash and then have some impact on that. So that's the mechanics. That's the movement of that water erosion. Next, we have the types, and there are three types of water erosion. We have sheet, we have rill, and gully. And so the biggest difference between rill and gully is that we can correct this rill erosion with some tillage, but once we form a gully, it can't be corrected. And you'll see this in the next couple of slides, the difference in kind of why we can't correct this gully erosion. All right, so sheet erosion, again, I just want to go back. The mechanics happen the same for all three of these. There is some detachment, transportation, and then there is a deposition. And so for sheet, that is moving all of the soil at the same time, kind of just as a continuous movement, or just sheet erosion, like a whole layer of soil just being removed. Next, we have rill. Many of us have seen this at some point in time. Water, finds the path of least resistance. And as you start to get more water movement, you develop a little channel. And then as you develop that channel, water will naturally seep to that. Look, it's going to this low spot down here. And so we have several of these channels, and each one of these are removing just a little bit of soil at a time. But 1,000 channels moving 1 little gram of soil is 1 kilogram of soil. And then as that starts to multiply, you can see where we lose soil very quickly. And so this can be fixed with tillage. At least on the surface, it can be fixed with tillage. This would probably need to be addressed. It looks like this is in some sort of bowl or some sort of depression. You would want to put some kind of cover on this to slow that impact of that rainfall. And this is where that interception comes in. And you'll see some of the means that we can use in order to minimize this rill erosion. And I mean, you've seen this constantly. You might have seen some netting or some pine straw or some regular, hay straw that is put on the ground in order to slow that water movement so that we don't get this detachment, transportation, and deposition. We want to keep our soil where it is. And then finally, gully erosion. And so, this not only has a problem here because it can't be fixed, but if you're driving your tractor and you get to this gully, what do? How do you get across it? No, so now we're taking the time that it takes and the extra fuel that it takes to get around this gully so that you can then now perform whatever function it is that you're doing on this side of the field. So, this looks like it starts up here somewhere. You can't really do too much to fix this. The easiest way would probably be to try and put some cover close to this so that we don't cave those edges in and that we get some root growth that is going to kind of stabilize this soil, but that gully is not going anywhere. You can't really fill it in either because the water has, there's nothing that's going to hold that soil in there. And then also the cost that it would take to put that much soil in that gully and just to have it run out anyhow. So the best fix would probably be go up the hill, find out where the water is starting, and divert that to a different area. All right, so if you've had Dr. Bayer's Ag Engineering Technology class, he's talked about the universal soil loss equation enough, but we still want to talk about that in soils and kind of go back over it a little bit. Because this is how we determine how much erosion we're going to have, and then we can predict, we can't predict how much sediment is delivered to the streams, but we can determine if our soils are in danger of, being eroded to the point that they cannot recover. And then, just because... and then you might also hear the term the Russell. And so this is the revised universal soil loss equation. And they have just really kind of improved the accuracy of that soil loss. So, they came up with the universal soil loss equation and said, these are the factors. And then as people started studying it a little bit more, scientists like to, make sure that we're getting every little component of that. And try and get down to an accurate value for soil loss. Now, this brings us to the T value, and this T value is really the threshold. This is different from the A. This is the T, this is the threshold, and this is how much soil can be lost without degrading the soil's long-term productivity. And so for the most part, most soils are going to have, a T value of, somewhere between 5 and 11. In Tennessee, I haven't seen anything above 5. I don't know that I've ever seen one that's like 6 or 7. So that would be interesting to see. And sometimes you'll see them even lower. Sometimes they'll be 3 because that soil is, prone to soil erosion, and we need to minimize that. Maybe it's a very shallow soil, and we don't have very much to spare. And so, this T value is going to be are typically 5 to 11 megagrams per hectare. Sometimes we get kind of caught up on what the unit is, but ultimately when we think about it, we just need to make sure that the A, which you'll see in the next slide, that A does not exceed T. It doesn't matter what the unit is. T is the threshold. The universal soil loss equation gives us the A value, and as long as A is less than T, then we're not in bad shape. I don't want to say that we're in good shape because 4.75 is less than 5, but man, we're still kind of on the border there. All right, so there are four main components to the universal soil loss equation. And so A is the value that we're looking for, right? A is going to give us the predicted soil loss. This is the dependent variable. And remember that we need to have A less than T. All right, so R is for rainfall. This is our rain-related factor, obviously. Next, we have our soil-related factors, and so this is the K is the soil erodibility, and this is going to have implications for the soil texture, the soil structure, how much organic matter is there. So this value is given. We have the length and the slope and the steepness of that slope. Next, we have cover and management and erosion control practices. And so, everything up here, our R, K, L, and S, are things that we can't really control. I can't change the rainfall. I can't change the intensity of that rainfall. I can't change the soil erodibility. Nor can I change the slope length and the steepness. But I can change the cover and management. I can change the erosion control practices to minimize the movement or the energy of that water moving across the soil. That's really what these two components are for. We're trying to slow down the movement of that water. Because remember that when rainfall intensity exceeds infiltration, we get runoff. So this cover and management and these erosion control practices go into the interception. How do we minimize the impact of that 18.5 mile an hour raindrop hitting our soil, detaching that soil particle, transporting that off of our property or our land area that we're used to, and going somewhere else? So these are the things that we can control. These are the things we can't. All right, so for rainfall erosivity, these are values. These are rainfall values, not the actual rainfall value. Like we don't get 350 inches of rainfall. But this R factor is going into, kind of the rainfall patterns and history of this particular region. And so, I am from right here. This is home for me. And so on the coast, we get a lot of rainfall. We can get heavy rainfall. We're right on the coast. So all that water is moved up into the atmosphere. It's very humid. But at some point in time, that water has to fall out. And so we can get very intense rainfall, rain events, and we get a lot of them. So for us, down here on the coast, our R factor is going to be 650 or 700. For us, where we are now, we're looking along this line. This picture is not very good. I have yet to find a good isohyadal map that I can use for this demonstration, but we're somewhere between 225 and 300, 275-ish, right? So these lines are, 225 right here, just one that's in between. And then for us, we're at about 200. Somewhere in there. All right. Next is the K factor, and this is the soil erodibility. And so if you take Dr. Baer's class, you'll hear him talk about Wishmeyer's K. And they have determined this for these research plots. And they've determined the K by how much infiltration capacity of that soil, the structure, which is ultimately determined by the soil physical properties. Like this is where Module 1 and the soil physical properties come into play. These things directly influence the K factor, which is a portion of minimizing soil erosion. So if we've got good texture, structure, all of these things are ideal, we're going to have a lower K factor or K value. So you might see soil erodibility, and for each soil series, there's going to be a K factor or K value. And so those with high K values are going to be more erosive. And because, most of that water is not going to move into those soils. We have blocky or platy structure. Remember that platy, that is just layered on top of each other, and that water has to move laterally rather than vertically down into the soil profile. Our low K values are going to have high organic matter, and they're going to have a good granular structure, so the pore space is going to be conducive for water movement into the soil. So this is going back to module 2.1, where we're talking about that we need that water to move through the soil profile. And so having the path of least resistance and those channels that allow water to move very quickly through that soil profile, that's going to have a low K value. Because remember that when rainfall intensity exceeds infiltration, so we have runoff. So the very top portion of our soils need to have this granular structure so that water can move into the soil. Next, beneath that, so like in our O horizon needs to have a very nice granular structure, be very open to like a sponge to absorb some of that water to bring it in, and then we need to have movement through that soil profile. And so that's why we want to rely on no-till management in order to develop this granular structure or this consistent structure. All right, so next we have slope length and steepness, and there's nothing we can do about this. But when we talk about our management and control, we can kind of minimize or slow down the water by changing probably the length of that slope. And so, this is just a table, right? So they've determined somewhere along the lines that if you have a slope this much, a 6% slope that's 75% long, your LS value is 0.69. All right, for cover and management, this is just a very simple table. It's just for demonstration purposes. You will find that as you move into maybe a career that looks at this, there are different combinations of crops and management factors that give you a different C value. Again, like I said, these are just for demonstration purposes, in that if we just did a fall plow and we remove those residues, think about that we don't have anything that's on the surface of that soil, and so there's nothing slowing that water movement, so we would expect to have a lot of erosion. If we don't till and we leave all of our residues, then we would minimize the movement of that water. All right, so the things that are going to help us in cover and management, we definitely want to put cover crops out there. We want to have not disturbing our forests or our grasses, because that's going to minimize the impact of that water or raindrop on that soil. And if we minimize the impact of the water, we slow down the energy of that, and we can get better infiltration. We definitely want to grow cover crops. Cover crops have a lot of benefits, but for the most part, they're going to keep our soil. That's that maintaining that living root year round. The cover crops also minimize the impact of that rainfall, and we get more interception. You got to think about water hitting this leaf blade and kind of rolling down through stem flow. And when you slow that water movement, remember that if we can minimize the rainfall intensity before it hits the soil, we can minimize our runoff because we're increasing infiltration. And then mulches. Again, this is just something that is going to minimize or soften the blow or the impact of that raindrop. Tillage is something that is what I found is that not a lot of people do conventional tillage around here, mainly because they know that they're trying to conserve that soil. But one of the, maybe in different regions, they're more accustomed to tillage than they are to no-till. So going into conservation tillage, in order to be considered conservation tillage, we need to have at least 30% of the residues left on the ground. So let's say that you take over a piece of land and you want to get in an NRCS conservation program. This is probably a number that you'll see again. This will be a standard in order to be considered as no-till or conservation tillage. And then under conservation tillage, we have different types of till. Again, most of us use no-till. One of the probably an up-and-coming or quickly being adopted is strip till. And strip till is just, as it sounds, you're just tilling the strip where you're putting the crop. And so we use this a lot in row crop production because we want to get the benefits of no-till, but we also want to get the benefits of conventional till right where our crops are being planted. So you can see that conventional tillage, this is tilling the whole soil. We break that structure up completely, and we have to start all over again, basically. And also, when we do that, the surface is bare. One at least movement towards better management is going to be a chisel till. You can see that it's disturbing that soil, but also at the same point in time, there's nothing left on top of it. And so you want to make sure that you leave some residues on top of that soil. You don't want to plow those under. This completely turns the soil. You can see we have residues here, no residues here. Water is going to hit that, and it is going to move that soil off of that field. Yeah, he should definitely not be plowing. This is going to minimize that water. You'll see this in the next slide. So again, 30% is going to control both the wind and the water erosion. So I want you to think about the movement of water. It looks like we're going to this kind of drainage ditch right here. The land is graded so that water slowly moves that way. And that as water has to travel, it is being intercepted or obstructed by this crop residue. If the water is not moving that way, then it must be moving through or into the soil. So now we're increasing the infiltration rate. So cover crops and leaving crop residues are going to increase the infiltration, which will reduce runoff. All right, next we have our erosion control practices. And so these are kind of some of the different cropping systems that we can implement inside of our cash crop so that we can minimize the movement of that water. This is actually going to change the flow and the velocity of that water. So for contour cropping, this is just going to be planting along the contour of the land. So like if you can think of a contour map, is really just going with how that land is laid out. And then strip cropping is something that we can do in order to shorten that slope length. So for contour cropping, they're kind of moving that water where they want it to go. And then also that they've planted this against the normal flow of water. Might be kind of hard to see here, but you can see that this portion of the land is a lot higher than this portion and that portion. So naturally, this water would want to run that way. And if we can channel this water, we can also slow the movement of that water across the whole field in order to get that maybe to, looks like they have a grassed waterway here. And what they're doing with this is they're using that grassed waterway as a means of minimizing or slowing down the water and allowing some of that soil to settle out of that suspension. Strip cropping, obviously we're going to have different strips of different crops, and that each different crop has a different impact on the movement of that water. And so if we can slow some of this water down, then we can minimize that minimize the impact of that water. Some other things that we can do are terracing. So there may be bench terraces or broad-based terraces. So when I'm thinking about this is, and you'll see this on the next slide, that we we are trying to hold on to our water. And I mean, if water were to fall here, it would instantly run down that slope. There would be no slowing that down. So, it's kind of like a cascading, kind of overflowing thing to where we're slowing that water movement. And then we're also getting some of that infiltration, or at least this looks like it's going to have very shallow soil. So we would want to hold that water there very long time in order to allow that plant to take that crop up. All right, so if we don't have any control practices, the p-value is 1. So this would kind of give me a quick indication that if I don't have any erosion control practices, my erosion is going to be very high. And so, again, this is something that we can look at. The lower the value, the lower the erosion potential. Because we're trying to get from a very high rainfall, like remember if we go back to that R factor, and we have a rainfall intensity of 300, we're trying to minimize that 300 down to less than 5. All right, so that ends module 2.2.2. In the next module, we will actually calculate the universal soil loss equation and finish up module 2 overall.